I share.
Yes, I will. I think I should schedule that, because bad thing about me is that I really forget. I have a weakness. So I remember you told me the same thing yesterday, and I didn't do it. But if I schedule it, like to do it tomorrow at a specific time, I know I'll be able to do it.
Okay.
Yeah.
And today's recording too.
Yes, I will. So yesterday we
Thank
were
you.
looking at the image of a matrix, um, and the kernel of a matrix. And then immediately after the lesson ended, important information came back to my mind. So I will start with
So
that.
we were doing we didn't do question 2C yet.
Yes, we
We were
did.
doing B.
Yeah. So we went back to, let me take you back to B.
Yes.
For those values of k such that Lk is not surjective, and so if Lk is not surjective, this means that its domain is not going to be, its image is not going to be equal to the codomain, right?
Yes.
And we also found out that if k is equal to -1, then L -1 is not surjective, right?
Mm-hmm.
And we also saw
Yes.
that L -1 can be written as 1, 0, 2, 1, 2, -2, 1, 1, 0, 0, -1, 2. I hope that's right. I just replaced k with
Yes.
-1. And then we can
Yes.
reduce, we reduce it. It becomes 1, 1.
1, 0.
Actually, there is no need to use, so I could just do 2 minus 2. 2 minus 2 is 0. -2 minus 2 is
Yes.
-4.
Yes.
0 minus 2 is -2. Then we have 2.
And 2. Yeah.
And then if we do twice this plus this, 4 plus -4 is 0.
0. Then it become
2 plus -2 is 0.
minus. Yeah. Yes.
-2 plus 2 is 0. Right?
Yeah.
And then if we divide by 1 by 2, this would become 1. This would become
1.5.
a half.
And -0.5.
And then this would become minus half. So first and foremost, we are doing all this to find the null space of the matrix. Of AK. Okay. We already know that.
Why? Yes.
What did I say?
I was saying, why do we need to find the kernel of AK?
Because we are looking for, we want to find a vector in R3 that is not in the image of LK. So if you are not in the image, you must be in the kernel. So if the vector is not inside the image, it has to be in the kernel of that matrix.
Okay.
Yeah. So finding a vector in the kernel is going to give us a vector that is not in the image. Okay.
Okay.
Yeah. So for us to find that, we just solve this. You solve this for 0 because you know the kernel is the set of vectors that is mapped to 0, right?
Yes.
So you just solve this for 0. So you could let x1 is pivot, x2 is pivot, x3 is free. So let x3 be S.
And x4
X4 is
be half a t minus half t. But it's not better to first put it in an equation so it's easier to understand. For example, x1 plus x2 plus x3 equals 0. x2 plus a half x3 minus a half x4 equals 0. So it's easier to convert. And now we just convert by x1, x2. So it is x1 equals minus x2 minus x3. And then x2 equals minus a half x3 plus a half x4. And we know that x4 and x3 equals s and x4 equals t. And we could, in the x1 equals minus x2 minus x3, we could put the x2 equation inside the x2 of x1. So it becomes x1 equals
a half x3
plus a half x3 minus a half x4
minus a half x4
minus x3
minus x3.
So it becomes x1 equals minus
a half x3.
Yes, x3 minus a half x4.
That's a half x4.
So kernel would be minus a half s minus plus minus a half t times t.
So
the kernel would be have two vectors, two bases.
Yes.
Which is s and t.
Yeah. So we're going to have.
So we have minus a half
s.
Then minus a half t. Yeah, minus a half s again.
So minus a half s. 0.
And 1 and 0.
Then 1.
1, 0, yeah.
And then 0.
0, yes. And then for t, it would be minus a half, plus a half, 0 and 1.
Can we write this as negative 1, 2, and 0?
Yes.
Then we can write this as negative 1, 1, 0, and 1.
And 2.
0 and 2.
We don't need 2 at the end.
And so any of the two. So if you want a vector that is not in R3, you could go with that, you could go with that, or they are linear combinations.
Yes. So, but that shows us that the kernel exists.
Yes.
So using k minus 1, we know that the kernel exists, therefore it is not in the image, therefore it is not surjective.
Yeah.
But the question says, for those values with the S, it's a plural. So how do you know when k, for example, if k equals 1, it might have a kernel?
If k equals 1, it's going to have a kernel, yes. But it's going to have a kernel, but it's going to be subjective. You know, being subjective doesn't mean that you don't have a kernel.
Oh, okay.
Yeah.
So how do you know if it's subjective or not? When it's subjective?
It's only subjective if the rank of your matrix is equal to its dimension. That is the only time it's subjective. No, wait. Can you ask your question again? No, I didn't get your question. Can you ask the question again?
How do you know when it is subjective?
It is subjective if the rank of your matrix is equal to the number of rows of that matrix.
So number of rows, okay.
Yeah.
And if it's not equal, then it is injective, or?
If it is not equal, then it is not subjective. If the rank of your matrix and the number of rows are not equal, then your matrix is not subjective.
Okay.
Yeah.
Okay, so we need to find a way that the rank is not equal to the columns.
To the rows.
To the rows, yes.
Yeah, and we only found that way by equating k to -1.
Yeah, but is there not like another way to, for example, let's say k equals 2, it might work.
No, k equals 2 is not going to work because we already saw in A that for every k not equal to -1, in A we only had 2 cases. The first case was when k equals -1. And in that case, the dimension of the image was 2 and the dimension of the kernel was 2. And then when k was not equal to -1, we had another case where the dimension of the image was 3 and the dimension of the kernel was 1, right? So for any other value k that is not equal to 1, the dimension of the image is equal to the codomain. And so for any other value k that is not equal to 1, Lk is going to be subjective.
Okay.
Yeah.
So the only solution to Lk to be not subjective then is k equals
-1. Yeah.
Okay. So the response will be k equals -1.
So
yeah, that's it.
The response is going to be k equals -1. Yeah.
And then they say find the vector R3 not in the image of Lk. But to be not in the image of Lk, that means that it is not subjective. So I just need to find a vector which is not subjective in the matrix A.
You just need, okay, you just need to look at the structure of your vectors. So take a random vector xy, take a random vector x1, x2, x3, x4, okay? And then if you take your random vector, let's see what's going to happen to it. It's going to be taken to R3, right? It's going to be x1 plus x2 plus x3 for the first entry.
Yes.
And then
x2 plus a half
plus
x3
a half x3
minus a half x4
minus a half x4,
and all 0 then.
and then 0.
It's
right?
a half x4.
And then 0, right?
Yes.
So your image, your matrix is taking vectors. Any vector is being taken to the image A, B, 0. Any vector is being taken to that image. It's going to be taken to the image A, B, 0.
Yes.
And so if you think of a vector that is not following this structure in R3, so if you think of a vector like 8, 9, 6, is this vector going to be in the image? You see, it's not following the format of vectors in R3, the format of the image, because this is what is contained in your image. A number, and a 0, right?
Yes.
So does this follow the same structure?
No.
So this vector is not in the image of LK.
But so the answer would be just a random.
Just a random vector that is not following this. That is not following this format. Yeah.
Okay. So if we check the answer,
Let's check. Question 2 C.
the answer said LK is not surjective when image LK is not equal to the three-dimensional, then that is for K equals -1. In this case, image L -1 equals column A -1 has dimension 2. So it is generated by any two linear independent columns. For example, C1 equals 102 transpose and C3 equals 110 transpose. And thus, for example, 001 transpose is not inside column A -1.
Yeah, you see the example they took? Remember I told you the structure in our image is A, B, 0, right?
Yes.
So in the image, you are allowed to pick a number, any number, but the last guy has to be a 0, right?
Yes.
So when they took 0, 0, and then they made sure the last guy is not a 0, that's a good example to show that the 001 is not inside the image of R. It's not inside the image of L.
But L, what is L? Is it?
L is the matrix, this matrix transformation.
Oh, so the matrix A in echelon form.
Yeah.
When K equals -1.
Yeah.
Okay.
So L is any of them. Oh, when I was pointing at this matrix, I thought it's the question. So it's this matrix is the same. Let me take you back to the question. This matrix?
Yes.
These two matrices are the same matrix. They are the same. Yeah, so L is that matrix. Whether in row echelon or in that other format, that's your transformation. And this is what L is doing. It's a function, right? So it's going into R. It's taking a vector from R4, and then it's taking that vector to R3, right? So if it takes a vector, let's say x1, x2, you see what we found here, x1, x2, x4, it's taken to a vector of the form A, B, 0, right?
Yes.
And it's not surjective. Not surjective means that it's going to take vectors into R3, but we are going to have other vectors that are not inside the image. So this is its image of L, okay? And the image of L is the one that has got vectors of this form, A, B, a number, and a 0 at the end, right? So if you think of a number that doesn't have a 0 at the end, then that number is going to be outside the image. For example, 001. If you think of another number like 896, you see? These are examples that are outside the image of L. L is a function. This is the domain.
Okay.
R3 is the codomain. And then the small circle in there is the image of that function L.
Okay. When they say, so the image is 3-dimensional.
Yes, the image is going to be 3-dimensional.
But a dimension is calculated from the columns minus the number of pivots.
Columns minus number of pivots?
Yes.
Okay.
So it wouldn't be 2 because
the dimension of the image?
Yes.
The dimension of the image is going to be 2 because you can see we have a number, another number, and then the final number has to be 0.
Yes.
Yeah.
Oh, so the image is 2, but why is the codomain not 2?
The codomain is R3. The range, the dimension of the codomain is not 2, it's 3. Because our function is taking us from R4, number of columns, and it's mapping every element to R3, number of rows. And realize the image of L is not R3, right? It's some space that is contained in R3. So the image of L is going to be your R2.
But okay, here it says let LK R4 go to R3. Be the linear map defined by LKV equals AKV. Is the line before the question ABC.
Yes, I'm saying it.
And this line, so R4 is the number
domain.
of the domain.
Yes.
With
R3,
the number of columns.
Yes, R4 is the number of columns.
And R3 is the codomain with the number of rows.
With the number of rows as its dimension.
But why does it change from columns to rows?
Because of matrix multiplication. Because when you take a matrix and then you multiply, this is 2. This is a 4 by 3 matrix, right?
Mm-hmm.
And then you're multiplying by a 4. It's going to be a 4 by 1 matrix.
Yes.
Right? A 4 by 1 matrix. Your answer is going to be a 3 by 1 matrix. So you started with 4 rows and 3 columns, right? And then here you have just 4 rows and 1 column. So you're going to end up with 3 columns and only 3 rows and only 1 column. So that's how matrices do. They move a vector whose dimension is the number of columns in that matrix, and then they transform it so that its new dimension becomes the number of rows. And that is why we do row by column multiplication.
Okay.
Yeah.
Is it not for the first matrix, the one you just wrote, which is 4 times 3? It's not 3 times 4, or is it we don't care about the order?
Three times 4. It should be like that. It should be 3 times 4, 1 times 4, and then 1 times 3. No, wait. A 4 by 3 matrix. A 4
So it
by
should
1
be
matrix.
3 times 4.
3 by 4
3
matrix.
times 4, then 4 by. Yeah.
And then 4 by 1 matrix, and then 3 by 1 matrix. Yeah. Because it's row by column.
Yeah. Okay. Understand. So should we try question 2C?
Yeah, sure. So they want us to replace k with 0. We get 1, 1, 1, 1, 0, 2, 1, negative 1, 2, negative 2, 1, 4. Am I right? Verify that.
So I'm a bit confused what you just did.
I said k equals 0.
K equals 0.
Yeah.
Then yes, should be correct. Yes, it is. But when they say span 4 minus 1, 1 minus 2, 3, 0, 1 minus 2, 2 minus 2, those three are the bases inside V.
The basis of a new vector space V. So this is
Okay.
taking us to a subspace of R4. And so they want us to take the matrix L, 0, and find a basis for its image. So they want us to go, this is R4, right? So inside R4, we have another space, V. Now V is this span. So they want us to use L as a function, and then they want us to map this V into R3. And so if we map it into R3, we are going to get its image inside here. And this is the image they are calling L0 of V.
Okay.
So to do that, we just map the basis. So you just take the 4, -1,
-1,
1, -2,
1, -2.
and then you find its
yes.
Yes, you could take the whole basis as a matrix. Also, that's another way. I was planning to do it separately, but let's do it as a whole. So 3,
3, 0, 1, -2.
1, -2. And then
-2,
2,
2, 2, 2.
2. And then you multiply these two matrices, and then you're going to get your new basis.
So we could do so 4 plus -1.
4 minus 1 is
4
3.
3.
3 plus 1 is 4.
1, 4.
4 minus 2 is 2.
2.
And then 0, minus 2.
0.
Minus 2 plus 1. Minus 1. Minus 1 plus 2. 3. Let me repeat. 0.
0.
Minus 2. Minus 2 plus 1. Minus 1.
1.
Minus
plus 2.
1. Minus 1 plus 2. Minus 1 plus 2 is 1.
So it's 1, yes.
And then 8. 8 plus 2 is 10. 10 plus 1 is 11. 11 minus 8 is 2.
2.
And then 3 plus
Then
0 is
this
3.
is
Plus 1, 4.
0.
So that's 2.
Yes.
And then 0, 0,
0.
1 plus 2,
2.
3.
3. Then
And
this
then
is 6.
6,
0.
7. 7 minus 8, -1.
Yes.
This is 4.
Then this is mine. Yes, 4.
4
Then
plus
0,
2,
4,
6 minus 2.
2, 4, 6, minus 2, 4. Then
Minus 2.
minus 4.
Minus 4 plus 4, 0.
0.
2
2,
plus 4, 6.
6.
So we have found a basis. So we are going to say that L not V is going to be span 2, 1, 2, comma, 2, 3, negative 1, comma, 4, 4, 6.
So those are the bases of L0V.
Yeah. Oh, did we check for independence of V?
Oh,
Span?
no.
We should check it because we have to verify that this is the basis first. They give us a
Yes.
basis, but we have to verify. You remember what we learned last time? We should always take those lessons with us going forward.
Yes.
So this is 4.
Always verify.
Yeah. So alpha 1, 4 plus alpha 2,
Minus
3
alpha 2
minus
alpha
3,
3
2
2
equals 0.
equals 0.
Alpha 1 negative 1 plus
0
plus alpha 2
plus
0
plus alpha 3 2
plus
equals
alpha
0.
3 2 0.
Then alpha 1 1
Alpha 1
plus alpha 2 1
plus alpha 2
plus alpha 3 2
plus 2 alpha 3
equals
0.
0. Minus 2 alpha 1
Plus 2 alpha 1
minus 2 alpha 2
minus 2 alpha 2
and plus 2 alpha 3 equals 0.
minus 2 alpha 3 0. Oh, that was an
Bless you.
attack. Thank you. It was unexpected. So can we say alpha 1 minus alpha 2? Can we say alpha 1 plus alpha 2 minus alpha 3 equals 0?
So we know that alpha 1 equals alpha minus alpha 2 plus alpha 3.
I wanted to say alpha 3 equals alpha 1 plus alpha 2. Right?
Yeah.
Then we go back up.
So, but in this case, you could we could we put alpha 3 inside every alpha 3 we have, so we know, for example, we could put alpha 3 inside the first alpha 3 we have and try to find what alpha 1 equals.
Okay, what do you mean?
For example, alpha 1 4 plus alpha 2 3 minus 2 times alpha 1 plus alpha 2.
Okay.
And then we try to
Alpha
know
1
what
4 plus
plus alpha 2
plus
3
3 alpha 2 minus 2 alpha 1
and yes,
minus 2 alpha 2
alpha 2
equals 0. So
yes.
this means that 2 alpha 1 plus alpha 2 equals 0.
Yes.
And so
we know that alpha 2 equals 2 alpha 1.
Alpha 2 equals negative 2 alpha 1.
Negative 2 alpha 1. Then we do the same with the other one. For example, the second equation. So and it would be alpha 1 minus alpha 1 plus.
So in the
alpha 2
let's do the third equation, because alpha 2 is going to be taken to 0.
Yeah.
So alpha 1 is alpha 1, right? And then alpha 2 is minus 2 alpha 1. And then alpha 3 is alpha 1. So this is plus 2 alpha 1 plus 2 alpha 2. But alpha 2 is minus 2 alpha 1. So this is plus minus 4 alpha 1, right?
Yeah.
Equals 0. So this only means that 1 minus 2 plus 2 cancel. 1 minus 4, that's minus 3 alpha 1 equals 0, meaning that alpha 1 has to be equal to 0. And so alpha 2 has to be equal to 0. And alpha 3 has to be equal to 0. So they are independent. We checked. And so our solution stands. Yeah.
So they are not independent. They are independent.
They are independent. They are not dependent. They are independent.
Independent. So they are bases.
So this qualifies to be the basis of V. And so what we found here qualifies to be the basis of the image of V.
So the span, so the thing we did before, which is multiply.
Yeah, it stands and it's right.
Correct. It's
Should be right.
Okay.
Yeah.
And if we check the response,
let's check.
Says L0V is the column space of the matrix A0, 4, 3, minus 2, minus 1, 0, 2, 1, 1, 2, minus 2, minus 2, 2. What? Why is the matrix A weirdly inverted?
4, negative 1, 1, negative 2, 3, 0, 1, negative 2, negative 2, 2, 2, 2. And then they did 2, 1, 3. And then 2, 3, negative 1. Where did they get 4, 4, 2?
I don't really understand how they managed to.
So at least we have something similar to that. 2, 3, negative 1 is there.
3, 1, yeah.
Then we have 4, 4, 2. So at least we have, okay, let's see. At least we have 2, we have 3, we have negative 1, we have 4, we have 4, we have 2.
And
So
we
we are
have 1.
missing 3. We have 2 and we have 1. So we are missing these 2.
Yes. Then they say the matrix has rank 2 since C1 plus C2 equals C3. So dimension L0V equals 2. And any 2 linear independent columns will form a basis. Example 2, 1, 3, 2, 3, minus 1.
So let's see. So they did A naught, they multiplied by those matrices. So let's check our work then. Let's check this number. And how did we get this number? We did this row times this. So this is 8, right? Minus 2 minus 1 is plus 2.
8 plus 2
This
plus
is 1
1
plus 1
minus 8.
minus 8. 2 plus 1 is
Oh,
3.
3 is not 2. Ha.
So let's check the other one. The other one was this one, right?
Yes. So it was
So
2 times minus 2 is minus 4.
2 times minus 2 is minus 4. Minus 2 times 2 is plus 4.
Sorry, minus 2 times 2 is minus 4.
Oh, okay, minus 4.
Oh,
So, yeah,
yeah.
that's the mistake I did. You see the plus 4? Yeah.
Yes.
So that's minus 4. That's minus 4 again. That's
plus 2
plus 2.
and plus 8. So it would
Plus
be 2. Oh, because we went too fast. We went from to do the calculation in the brain without
Yes.
writing.
Yeah. That's the problem. Again, it's a lesson learned, right?
Yeah.
But right now we are allowed to do it fast because we know if we fail, at least we can correct ourselves. And we are also saving time. So there you go. So next, remember I told you to check for independence for V. So you have to check again for independence here. You have to check for independence.
Okay. So we need to do again 2 alpha 1 plus 2 alpha 2 plus 4 alpha 3.
Yes.
Equals 0.
Actually, no need. Look, 2 plus 2.
Oh, yeah.
2 plus 2,
4,
4,
4,
right?
3 is dependent.
Yeah, 2 plus 2, 4, 1 plus 3, 4, 3 minus 1, 2. So cancel him out. He's depending on these two. And so the basis is going to be 2, 1, 3.
And 2, 3, 1.
And 2, 3.
Minus 1.
Minus 1. There you go.
Perfect. Okay.
Yeah.
So let's do question 3A, which says, consider the matrix. Okay, determine an orthonormal basis of R3 consisting of eigenvectors of A.
So you need to find eigenvectors of A. And then once you find them, you need to use Graham-Smith orthogonalization process to orthogonalize them. But eigenvectors will always be orthogonal. I believe so. So you don't even need Graham-Smith. Once you get your eigenvectors, you just make them equal to 1. Their length should be 1, and that's it.
Then let's try it. So
yeah.
To find the eigenvector, the equation is, first of all, we need to find the eigenvalue of A before finding eigenvector. So the eigenvalue is the determinant of A minus alpha or minus lambda identity equals 0.
Yeah.
So we know that A minus lambda identity is 1 minus lambda minus 1, 0, then minus 1, 1 minus lambda, 0, then 0, 0, 2 minus lambda. And the determinant of this is so it would be minus 1 lambda, sorry, 1 minus lambda, minus 1, 0, minus 1, 1, 0, 0, 0, 2 minus lambda. So it would be 1 minus lambda, determinant of 1, 0, 0, 2 minus lambda, which would be 1 minus lambda, 2 minus lambda minus 1, so it will be plus 1. It's 2 minutes, minus 1, 0, 0, 2 minus lambda. So it will be 1 minus lambda, 2 minus lambda, plus minus 1, plus minus 2, minus lambda. So it will equal 2 minus lambda minus 2 lambda minus plus lambda squared minus 2 plus 1 minus 4 plus 2 lambda plus 2 minus 2 4 lambda minus 2 minus 1 minus 2 minus 1 plus oh wow, you already got it. Lambda equals 0 and lambda equals 2.
Yeah. Did you get that?
No. I got a third degree polynomial.
Yes, even my polynomial is third degree. Can you give me your third degree polynomial? Just give it to me.
So I got lambda cubed
Okay.
minus 5 lambda squared plus 6 lambda minus 4.
Plus 6 lambda minus 4. Like that?
Yes.
Can you check the solution and tell me whether lambda is 0 and 2?
So
The eigenvalues.
so the eigenvalues are 0 and 2.
That's what the solution says.
Yes.
Okay. Yeah, I just wanted to confirm because I don't want to explain and I'm wrong, you know. So I know what you did. I know what you did. You just computed the determinant. You did 1 minus lambda. So you did 1 minus lambda, right? The determinant of 1 minus lambda, 0,
Yes.
0, 2 minus lambda. And then
Yes.
you did plus 1, and then 1, 0,
Yes.
0, 2 minus lambda, right?
I did minus 1, 0, 0, 2 minus lambda.
Minus 1 or minus 1, 0, 0, 2 minus lambda, right?
Yes.
And so this gave you 1 minus lambda, 1 minus lambda, 2 minus lambda, right?
Oh. Wait. Oh, I did a mistake. Oh,
Okay.
I forgot the lambda, the 2 by 2 lambda. So the second 1 minus lambda.
Oh, okay.
So I did 1 times 2 minus lambda, not 1 minus lambda times 2 minus lambda.
Oh, okay. And then here you should have done minus 2 minus lambda equals 0, right?
Yes.
If you factor out 2 minus lambda, you should get 1 minus lambda squared minus 1, right?
Mm-hmm.
If you expand 1 minus lambda squared, you should get 2 minus lambda, 1 minus 2 lambda plus lambda squared minus 1. The 1 and the minus 1 cancel. You're left with 2 minus lambda, lambda squared minus 2 lambda. You factor out lambda, you are left with lambda, 2 minus lambda, lambda minus 2.
Yes.
But that is a long method, whatever, because I was trying to do it the way I think you did it. It's okay, it works, but it's long. You should have switched your rows to make it short.
But how did you get? So you did also a bit like the same way I did.
Yeah, but mine, I brought this row up. I did 0, 0, 2 minus lambda, and then everything went down. 1 minus lambda, negative 1,
okay.
0, negative 1, 1 minus
so
lambda.
You switched the rows.
0, yeah, I switched. And so I could see 0 times that, 0 times that, I don't care. So I just picked him. 2 minus lambda. And then this determinant, 1 minus lambda, 1 minus lambda, multiplied by 1 minus lambda, minus negative 1 times negative 1, 1. There you go.
Yes, that's a way to. Yeah, I didn't think about that.
Yeah. So usually whenever you're looking for determinant, always use the row that has the largest number of zeros. So I looked at row 1, it has 1 0, row 2 has 1 0, row 3 has 2 zeros. So I brought it up, and then I knew it could make my computation faster. So we find the eigenvector,
yes,
associated with 0.
But there's 2. So the algebraic multiplicity of eigenvalue 2 is 2.
Yes.
Okay.
You're a good student. You remember things. So this is going to be the same guy. 1 minus 1 0.
Yeah.
Minus 1 1 0. 0.
Yeah. So the equation
0,
to find
2.
the eigenvector is a minus lambda identity, everything times by the vector. Yes. Equals 0.
So you can see that 2z is 0, right? So first of all, z is 0. And then negative x plus y equals 0. And so x equals y. So,
yes.
So one eigenvector is going to be 1 1 0. The one associated with the lambda equals 0. Right?
Yes.
And then the other eigen guy.
The other one would be.
Yeah, it's going to be 1 minus 2. What is 1 minus 2? It's negative 1. Negative 1. 0.
1 0.
Negative 1. Negative 1. 0. 0 0 1. Oh, 0 0 0.
So it would be negative 1 equals y. For negative x equals y.
Negative x equals y.
So it would be minus 1, 1, 0.
And then 0z equals
Equals
0,
0.
right? So z can
Yes.
be any number, right?
Yes.
And so the
So
other,
how would you write this?
so I'll just pick 1 to be y, then negative 1 would become x. And then I can
Yes.
write any number for z.
Or could I write like a letter, like k, which would be any number?
Yeah.
But would
Like
this be
k,
correct?
where k is any number.
Yeah, I need to write, okay, k is any number. Okay, so the eigenvectors of those two are of A. And we need to determine an orthonormal basis of 3.
First of all, let's check whether they are orthogonal. Negative 1 times negative 1 is negative 1. 1 times 1 is 1. K times 0 is 0. Their dot product is 0, so they are orthogonal. Remember I told you eigenvectors will always be orthogonal. So we just need to make them orthonormal. So the length of this vector is square root of 2. So multiply by 1 over square root of 2, and he becomes of length 1. Okay.
Yes.
And then the length of this other vector is 1 plus 1, 2. 2 plus k squared. So it's going to be 1 over k squared plus 2 square root. And he's also, so this is orthonormal. Let's see. Number 3 solutions. Yay, exactly what we have. Huh?
Wait.
Oh. Oh. I see. Oh no, every mistake every time. So this is okay. This one is okay, right? But this one is not because of z. Remember, z was free, right?
Yes.
So you let z be equal to s. Negative x and y, they have nothing to do with z. So they are going to form the basis negative 1, 1, 0, because they are not functions of z, right?
Yes.
And then the other one is going to be 0, 0, and then our z, 1. So we are going to have that one, and then this one, and then we can normalize it by putting 1 over square root of 2. Like that. You see
but they wrote 1 divided by square root of 2, then minus 1 divided by square root of 2 and 0.
It's the same thing. That is the same as this one. Because remember, a basis has to be dependent, right?
Yes.
If we want to choose a scalar negative 1, we would generate another basis, 1 over square root 2, 1, negative 1, 0, which is the same as what they have in the answer. So the two are the same because they are they are dependent. They are scalar multiples of each other.
Okay.
Yeah.
So could we redo again?
Okay.
Just to be clear. So just to recap, when there's a free column or row, that means there's another basis with only the free column, which is Z.
Yeah.
So when Z equals 0, Z could be any number.
I guess
Cannot be associated with numbers.
the best way we could have done it, let us just take it all over again. If we take it all over again, we are going to see it. So, oh, I wanted to reduce it, but you can't reduce it. So at this point, you can see that x equals negative y, right?
Yes.
And then z equals s. So there is no relationship between x and y and z. X and y have a relationship, but they are not related to z, right?
Yeah.
And so you could say 1, -1, 0. This is x, negative y, and z. Z is nothing.
Yes.
And then z is not related to xy. So where z is going to be found, there will be no x and no y.
Okay.
Yeah.
And to normalize them, they need to equal 1. The length needs to equal 1.
Yeah, the length needs to be 1.
So therefore, we need to do square root of 1 squared.
Yeah.
Plus 1 squared, which would be square root of 2. Therefore, we divide by 1. So it's 1 divided by square root of 2.
Yes.
Okay. Okay, so determine an orthonormal basis of R3 consisting of eigenvectors of A. It would be, oh, where's the other one?
The other basis?
Oh, there's a basis missing.
Yeah, the basis that was related to 1. The basis that was
0.
related to 0.
Yeah, what was it? It was
So
1, 1, 0.
We generated it with this.
Yes.
So we found that 2z is 0, meaning that z has to be 0 always, right?
Yeah.
And then x is equal to y, so it was 1, 1, 0. And so we had to also normalize it by dividing by square root of 2.
Mm-hmm.
Yeah.
Okay. Understand. So we could go 3B. I think once we finish this paper, those are about conics. 3B.
Yeah.
Yeah, I did some conics. The last lectures were about conics.
Oh, okay.
But it's very broad. It's not something that I know by heart. Yeah, I was saying once we finish this paper, we should redo everything again, but very quickly. To know if, or I should redo everything again.
Yeah. We can redo everything again to master. Like, what conic is this going to be?
So
x
consider the
squared.
conic C of equation x squared minus 2xy plus x plus y squared plus square root of 2x plus 2 equals 0. Reduce the equation to canonical form and determine what type of conic it is. So, by heart, I don't know how to do it, but if I just look at a paper that I have, then I know.
Mm.
Because it's because I finished geometry lectures.
Oh, okay.
So I finished linear algebra and conics too.
Yeah.
And so the conic were the last topic, which I didn't revise yet.
So first of all, this one is not a circle.
How do you know that?
Okay, first of all, I know that for a circle, you have to have x minus a squared plus y minus b squared, and this has to equal the radius of that circle squared.
Mm-hmm.
Can you remind me the equation of an ellipse?
Equation of what? Sorry.
Ellipse. You know, for conics we have 4 of them. It could be a circle. It could be an ellipse. It could be a parabola. So first of all, this is not a circle, and this is not a parabola. It could be either an ellipse or a hyperbola. What is the equation of an ellipse? Let me check to remember.
I have a paper here. Maybe this is correct.
Mm-hmm.
It says so Z1 squared, which would be point X of the center.
Mm-hmm.
Z1 squared divided by alpha squared plus Z2 squared divided by beta squared equals 1.
Okay.
Where Z1 and Z2 are the center.
Z1 and Z2 are the center.
Yes. So if we take, for example, using A and B, which should be the center.
Yeah.
So
let me use H to be my center.
Okay.
And then K, H and K to be my center.
Okay.
Divided by B is usually the major axis. A is the minor axis. That should equal 1.
Yeah.
And then for the hyperbola.
Hyperbola would be the same thing, but just with a minus.
Same thing, okay. But just with a minus, so x minus h squared over b squared plus y minus k squared over a squared equals 1. So first of all,
hyperbola is minus in the middle.
Oh, minus. So first of all,
it says equals plus and minus 1.
Equals plus or minus 1 here?
Yes, it says on my paper that I have.
Okay, so these equations, they are going to guide me. For example, I'm going to pull the 2 out. I have x squared plus 2xy plus y squared plus root 2x equals -2. Okay.
Yes.
And then could try to complete a square. I could try to have x squared, bring this guy in, square root of 2, x. And for me to complete the square, I would have to divide this by 2 and square. It's going to be a half. So I add a half to that side, and I add a half to the other side. And then I have plus 2xy plus y squared equals a half minus 2. It's going to be 1 minus 4, negative 3 halves. And then now I could write this as x plus a half squared. And then I have plus 2xy plus y squared equals negative 3 over 2. The fact that we have an xy in there is going to make matters very, very, very complicated, but let's keep trying. So you have y squared plus 2xy. You could do plus, divide that by 2, you get x. If you divide that by 2, you get x, you square it. And then once you square it, remember to subtract x squared from one side. And so this is going to be y plus x squared. This is deadly. So x plus a half squared plus y plus x squared equals negative 3 over 2 minus x squared. So it's going to be, it's probably an ellipse. Let us just see how they reduced it, because the xy is bringing us trouble. But because I can see a plus is showing up, I would go with the ellipse, but maybe the negative sign would make it be a parabola, but I'm going with the ellipse.
Is it not like a technique to use to find out if it's an ellipse or parabola or
Yes,
circle?
this is the technique I was using, trying to complete the square.
Oh, what do you mean by completing the square?
I was trying to rewrite this equation back into one of the original forms. I was trying to rewrite the equation back. You see what I was trying? I was trying to bring it back into the original forms. But it wasn't so easy because of the 2xy in there.
As I remember, I'm not sure, but we took only the quadratic part, which would be x squared minus 2xy plus y squared. And we did something with this, and then something with the other ones, which is square root of 2x plus 2. No, we did only with the quadratic, then only with the linear, which is square root of 2x, then the constant. So we separated the equation in 3 bits.
Okay.
And I need to look up.
That is one way of doing it. You can see even here they used completing the square method. Right?
Yeah. Yes.
Yeah. We can pick the discussion from here, right? And then in the next lesson we can look at it, and then we can go back and master everything on this paper, and then move forward from there.
Okay.
Yeah.
Is it the end of the lesson?
Yes.
Oh, already.
You know, it wasn't so long. Remember, I returned your 30 minutes. So it was just 1 hour,
Yes.
30 minutes. Yeah. Linear
Yeah, I'm
algebra.
used to.
Linear algebra is very
Yes.
interesting. You never know how time flies. You know, even
Yeah.
when I'm teaching you, I don't feel as if time is moving because it flies. Yeah. So we can start from, we have a lesson tomorrow, do we? I don't know. Are you there? Hello, Claudia?